Hello everyone, and welcome to our next online lesson. I want to encourage all of you to vote tomorrow. This is one of the most important elections in the history of this country. I hope you get out, and I hope you take advantage of your American ability to vote. Be sure to wear a mask and proper protection. You'll notice I'm not wearing a mask, and that's because I'm shooting this at home in my home studio. If I were at school, I would still be wearing a mask. You should wear a mask at all times when you are outside, just in case somebody should come up and get closer to you. Last class, I talked about Albert Einstein and the constancy of light speed. And according to Albert Einstein, that the speed of light or electromagnetic waves was the same to all observers in inertial frames of reference. That if there were no preferred frame of reference, if there were no ether, and that was certainly what the experimental evidence was suggesting, light was different, did not need something to carry it, and that meant that things had to change. If the speed of light didn't measure out to be the same for every single person who measured it, then that would mean there was a way of telling how fast you were really moving, and that would mean that there was a preferred frame of reference. But there isn't. So what he then investigated was, if the speed of light is constant, what do we expect to happen because of that? And the first thing I want to go through is something called a light clock. If the speed of light does not depend on the person observing it or the source of the light, then it's always the same, and we could use it to make a clock. Now, a clock needs something that's absolutely repeatable as what we call the time base. For a pendulum clock, it is the spring of a pendulum. For a mechanical watch, it's this vibrating spring and wheel that is inside there. For a light clock, we use the fact that the speed of light is 186,000 miles per second. And what we do is we construct, it has to be a large clock initially, though it can be made much smaller. We start with a mirror. And then, it seems like a long distance, but it's really not that far. 93,000 miles away, we have a photo flash, a device that can make a bright flash of light, and the light travels out and then travels back, and then we have a telescope that can look in the mirror and detect the flash of light. Now we have this hooked up to a counter, a clock. Okay, we have it hooked up to a clock, and the way this works is it sends a flash of light. When it sees it comes back, it increments the clock 1 second and then sends the flash again. So it's pulse, 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 pulse. 2 times 93,000 is equal to 186,000 miles. So it would take the light 1 second to come out and then come back. Half a second out, half a second back. And we will suppose that I am here with this clock. So I'm standing here with this clock. And I also have a watch on my hand. So I have a watch on my hand here. And what I do is to adjust this clock, every clock has to be adjustable so you can make it keep correct time, is I have this mirror moved back and forth until the two clocks keep perfect time. If you move the mirror out, it runs slow. If you move the mirror in, it runs fast. So by trimming the distance to the mirror to exactly the right amount, you can make this clock synchronized with my clock. And we are here in an inertial frame of reference. Now, that's simple enough. You could make this fit on a table, but then the clock would tick in billionths of a second rather than entire seconds. Conceptually, it's easier to imagine a very large clock. And certainly 93,000 miles actually isn't that big. The moon is a couple of 100,000 miles away, so we could make this out in space easy enough. What gets interesting is what happens if the clock moves. What happens if you are in an inertial frame, which means you're not accelerated, so you can say, I'm not moving. What if I am in an inertial frame? I make measurements and I determine that I am not accelerated. As far as I am concerned, you're moving. As far as you are concerned, I'm moving, and there's no way to tell who is and who isn't. All we know is that one of us is moving relative to the other. From your viewpoint, you see me and the entire clock flying by, and let us make this a very high speed. This has to be near the speed of light, 186,000 miles per second, or 670 million miles an hour. That's incredibly fast. So you can suppose that I'm going a substantial portion of that. Well, you see the clock, me, and everything moving like this, moving along. And what you see, if you had some fog in here so that you could see the light beam, when the light flashes, what we see is the mirror and the rest of it move along, and at some point later in time, the whole apparatus and me is over here, and then at some point later on, it's over here. Like that. I'm just not drawing in all the rest of it. The key feature is this. When the light leaves and heads towards it, it leaves diagonally and the light travels like this. Hits the mirror just happens to arrive there, and then it comes back like that. Imagine that this is a train and I'm tossing a ball back and forth to somebody and you watch it from above. To me, the ball goes back and forth. But to you, the train's moving this way. You see the ball pace a diagonal track. So you see the light travel farther. Out and back is a hell of a lot shorter than way out here and way back. When the clock is moving, by the way, my clock is moving too. My clock is moving too. So let's finish these out. Here's that clock. Here's the light clock. But I am moving with this. You see me moving as well. This is going to be a key point. And you see the clock on my arm, my watch, moving as well. What has happened here is that the light has traveled farther. But, according to Einstein, the speed of the light is not affected by the speed of its source. If this were me and somebody else throwing a basketball back and forth on a train going like this, and you look down on it, you would see the basketball going faster. In fact, if I don't even throw the basketball, you see the basketball and me flying by maybe at 60 or 80 miles an hour. The speed of the train affects the speed of a basketball if we're playing catch. But according to Einstein, this is not the way light behaves. The light travels further, but not faster. If I tell you to drive further on a trip, but I don't allow you to travel any faster, the trip takes longer. If you travel farther, but you do not travel faster to compensate, then the trip takes longer. This means it takes longer for the light to get back. As a matter of fact, what would happen if the clock were going light speed? If the clock were going light speed, the light would leave here, but this mirror would be running away from it at the same speed, light. This would try to get closer to that mirror, but the mirror is running away so fast it can't catch up. The light would never make it back. That means the clock would stop. If the entire thing were going light speed, the light could never make it back and be received again. The clock would never tick again. What we have here is that a moving clock runs slower. It would stop at light speed. As ridiculous as that would sound, okay? The moving clock runs slower. What about, we can see that the light clock runs slower because the light must travel faster, must travel farther, but not faster, so moving clock runs slow. What about my clock? What about my clock? I am in an inertial frame. I can claim that I am sitting still. As far as I am concerned, I am sitting still and I see the light go straight out and straight back. Nothing whatsoever has changed. The clock is still keeping perfect time with mine. If I see this clock and that clock keeping perfect time, but you see that clock run slow, then you must also see my clock run slow. Which means we can dispense with the light clock and simply say that if I move past you very, very fast, you will see this clock ticking slower. You will see my heart beating slower. You will see me aging slower. I won't be aging as fast as you. And as I approach light speed, it's almost like you'll see me aging at a millionth of my normal aging process. You would see me live 1,000,000 times 100 years rather than 100 years. Yet to me, I am in an inertial frame. As far as I'm concerned, everything's fine. But when I look at you, as far as I'm concerned, you're moving. And I see your clocks running slow. You never see the clock running fast. You see it running slow. The effect is always to slow time. When I look at you, I'm in an inertial frame. I cannot tell if I'm moving. There's no way. There's no ether. So as far as I'm concerned, I'm living perfectly fine in my world. I'm aging at a normal rate. And you see me, though, aging slower, but I see you aging slower. I see you aging slower. This effect on time is called time dilation. Time runs slower, passes more slowly in a moving frame of reference. And this is called time dilation. Dilation means to stretch out. And you can actually work out exactly how much slower time will be passing. It would stop at light speed, which means, this is one of the first indications that nothing can actually go or exceed the speed of light. The speed of light is a fundamental speed limit in the universe. If you supposedly went faster than the speed of light, you might think the time would go backwards. Well, it can't. It can't. A moving clock runs slow. It would stop at light speed. Nothing with mass can go light speed, because time would stop, and that's not possible. Nothing except light, which is a wave, can go light speed. The lack of an ether leads to this inescapable conclusion. Now, it sounds absurd. You mean if I'm moving here back and forth like this, that my clock is running slower? Technically, it is. But the change is so utterly small, it's absolutely undetectable. You have to be going near the speed of light for these effects to be noticeable. Or you have to have an incredibly accurate clock. The direct experimental proof of this, we got to prove it, right? We assumed the speed of light was constant. This is one result. Well, now you got to prove it. Prove that it happens. Prove that it happens. Well, the most direct proof we have today is several experiments that have been done where they take two atomic clocks. Now, these are clocks that are so accurate that they won't slip out of sync even 1 second in like 300 million years. You synchronize these two clocks, and they are so accurate that they will not slip out of sync even 1 second in 300 million years. And then, so you synchronize them. Then you take one of them, and this is not easy because you can't really disturb. You put it in a plane, and you fly it around, and they did this. The plane flies around for something like a week. Now, planes only go 600 miles an hour, so the effect is going to be small. Nonetheless, you fly it around for, say, a week. You hire a plane to fly and stay in the air for an entire week. You fuel it from the air. Military can do that. They did that. You fly it around for a week, and you bring it back, and you find, when you bring it back, you find that it has permanently lost time. That it's a few billionths of a second behind the other one. And furthermore, it stays behind. So they're perfectly synchronized before you fly the one around and bring it back. You discover that this one is behind, and it stays behind after you let it sit. Accelerating the clock has slowed the clock. Folks, this is real. This is real. It means, for instance, this is a time machine. If you can build a ship and get on the ship and fly away from the earth very, very fast for a very long time and then fly back, you'll discover that because of time dilation, the people on earth will look at your ship and see your clock running very slowly. Maybe a millionth of the speed here if you get going fast. And then you come back. 1 year has passed here on earth, but 1 year passes on the ship, and 1,000,000 years pass on Earth. You come back 1,000,000 years in the future. Incredible. This is real. There are numerous other experiments that show that this is real. This is reality. Time is relative. Isaac Newton assumed that time was absolute. Turns out he was wrong. Time is relative. It's not an absolute. It passes differently for different people in different frames of reference. Verified again and again and again by experiment. In fact, there are some places where if you don't take this into account, it just won't work. If you don't take this sort of thing into account in some situations, your scientific apparatus simply will not function. It's so sensitive that it will not work unless you take this into account. What else comes out of this? Well, there's another way to look at it. If we imagine a ship traveling very fast, crossing our solar system, here's Earth, and here's a rocket ship that's been coming in from some, ET, going very fast. If we look at their clocks are running slow. If they look at our clocks seem to be running slow. I shouldn't say seem to be running slow, are running slow. Now we watch them zip by. We watch them zip by. And let us suppose that they're headed in a direction towards a faraway star, way out here. Here's Sirius, a star in the constellation, near the constellation Orion. Okay? Now to us, we've measured the distance to Sirius. And to us, we say that it would take 26 years for a ship at light speed for this ship to read it. It's almost light speed. So we watch this ship going very near light speed, and it might take, 27 years, because it can't actually go light speed. So it takes about 27 years for it to get there. We say that the distance to the star is 26 light years. A beam of light, a wave of light, takes 26 years to get there. But what do the people on the ship see? They see this planet whisk by. Okay? And they see it whisk by at almost light speed. They see it go by at almost light speed. And then they look out and they see that star out there, and to them, the star is coming towards them. Sirius is coming towards them. To them, they are not moving. Notice, do I have any fire coming out of the back of the rocket ship? No. The rocket ship is coasting. The law of inertia keeps it moving. It's coasting. It's in an inertial frame. It is in an inertial frame. So they see the planet whisk by. They see the star coming this way, and depending on their speed, they might see this thing come by in a year. 1 year later, we watch them. We watch them, okay? We watch their clock, and we say, while they're traveling, because of time dilation, their clock only ticks 1 year. What do these people say? Planet Earth flies by. They say the planet Earth has gone by. They're watching their clocks, and they say, there goes Sirius 1 year later, because of the time dilation. They say that the distance out to Sirius is not 26 light years, it's 1 light year. On board, to them, the distance is 1 light year. One light year. To us, the distance of the star is 26 light years. Who's correct? Who's correct? Both of them are. Both of them are. These people see the star coming towards them at near light speed. 1 year it flies by. It's 1 light year away. We see them fly by going near light speed. We measure the distance and say it's 26 light years. Both are correct. Okay? The distance is contracted. It shrunk. It is shrunk. It is shrunk. Isaac Newton said that the distance between things is absolute. Now we find out it is not. It is relative. This effect is called length contraction. Length contraction. A careful analysis of this shows, it's kind of strange, is that length is contracted or shortened only along the direction of motion. Only along the direction of motion, not perpendicular to it. That means that if you were to watch this rectangular eraser and it starts to go very, very fast, that you will see that it will be shorter and that there is some speed where it would be a square. And as weird as it sounds, it's not that it looks like a square. It is a square. It is a square. These are not illusions. These are real. These are real. You would see me, my same height, but I would look skinny. I would be skinnier than I would normally be. My height would be the same, but if we were moving this way, I would appear to be less wide than I am. Though, according to me, looking at you, you seem to be moving. As far as I'm concerned, if I'm in an inertial frame and I'm not accelerated, everything is completely and totally normal. There's no way to prove who is moving. I look at you, I don't see you made fatter. You are scrunched up. You are contracted. You are the people that are moving. Your time is going slower. Folks, this is real. We have done experiments that show that this truly happens. And for instance, in CERN, you might have heard of the big atomic particle accelerator in CERN. They must take into account this change in length as things go faster. Otherwise, the accelerating machine does not work. At that machine, they can accelerate things almost to the speed of light, and these effects become very, very important. To us in our everyday world, we don't notice this. These are so tiny that we never see them. This is why Isaac Newton thought that distance was absolute. Distance is not absolute. Distance is relative. Time is relative. Okay? And finally, there is another one. One of the things that Einstein works out is when he starts to consider energy. Let's also put up here time dilation. Let's get them all up here. Time is slowed by relative motion. A moving clock runs slow. Length is contracted only along the direction of motion when you start to go fast enough. Technically, it happens even when you're going slow, but the percentage is so tiny you can't possibly measure it. You have to have, again, incredibly accurate clocks or incredibly accurate rulers, which we do have, by the way, in the advanced laboratories. But in your everyday life, you're not going to notice these things. All right? Time dilation. Time is slowed by relative motion. Moving clock runs slow. If you remember, Newton had three absolute fundamental quantities: time, distance, and the third one, mass. He assumed that all three of those were absolute and invariant in the language that we used early in this subject. They're invariant. Now we find that length is relative. We find that time is relative. When you start to look at the acceleration of an object, you discover something weird when it gets near the speed of light. According to work and energy, when you do work on an object, it's supposed to increase its kinetic energy. In fact, the net work done on something equals the change in its kinetic energy. But when you work that out, getting near light speed, you discover that it doesn't seem to work. The object can't go the speed of light and can't pass it, and so as it starts to approach the speed of light, it doesn't speed up like it's supposed to. You apply a force to it, but it doesn't accelerate like it's supposed to. What's going on? When you work the math, you discover that when you start to get going fast enough and you apply a force to an object according to Newton's second law, it's supposed to accelerate. And it does, but not as much as it's supposed to. Conclusion: the mass of the object becomes larger as it starts to approach light speed. Mass increases with relative velocity. The faster it goes, the more massive it becomes, and in fact, it would be infinite at light speed. If you could get it going light speed, its mass would be infinite, which means you can't get it going light speed. It means that as it goes faster, it becomes harder to make it go even faster. Down at our velocities, you increase the force, you increase the acceleration. But when you get near light speed, you increase the force, you don't increase the acceleration, you increase the mass. The work is used to increase the mass. So here's another reason that you can't go light speed. It would take an infinite force to push it right over that limit and get it to go exactly light speed. You cannot have an object with mass going light speed. Mass is relative. Mass is relative. And I can do an experiment in one of our labs showing that this is true. Because even here at Frostburg State, I can accelerate small particles almost to the speed of light. And if you get them going fast enough and you try to steer them, say with an electric or magnetic field, they are sluggish. They don't steer as easily as they do at lower velocities. They're harder to steer. They're harder to accelerate. You can actually measure the increase of their mass. These things have all been verified by experiment, which means as I go faster and faster, my mass increases. But once again, if I am moving extremely fast but not accelerated in an inertial frame, I feel fine. Everything is normal to me. But you see me scrunched up, you see my mass much larger, you see my time running much slower. What do I see? I see your time running slower, I see you people scrunched up, and I say your mass is higher. Because neither of us can tell, if we are in inertial frames, who is really moving and who isn't. As bizarre as it sounds. Totally, totally weird, but verified by experiment. Now, it's easy enough to say who cares. So let's just summarize things here. Who cares? If this only occurs in the laboratory, what do I care about it, okay? What do I care? What effect does it have on me? Here we have Newton. 1687. Time, distance, mass. Absolute. Or invariant. But now we find in 1905 by Albert Einstein that time, distance, mass are not absolute and invariant. They are relative. Newton thought that time, distance, and mass were the same for everybody. They are not. When you move right respect to each other at very, very high speeds, which we can now achieve in the laboratory. Now, we don't have spaceships that can go this fast, but we can easily move atomic particles and atoms this fast. We find that time, distance, and mass do not remain the same. They are relative. They are relative. Now, what does this have to do with us in everyday life? Well, this one in particular is going to be extremely important. When Einstein analyzes this situation and looks at what happens to an object as we get it going faster, recall that kinetic energy is 1/2 mv squared. The kinetic energy of an object, its ability to perform work by virtue of its motion, is 1/2 of its mass times the square of its speed. Now, according to the energy theory, the total work done on an object is equal to the change in the kinetic energy. So that when you take into account all the forces acting on an object, and you calculate the work done by each one, we're going all the way back now to our energy idea, that when you add up all the work done by all the forces, that changes the kinetic energy. If you do positive work on an object, you increase its kinetic energy. Well, how do you increase kinetic energy? You increase the velocity. That's what happens in our little world. The engine on a car does work on the car speeds up. The rocket engine on a rocket does work on the rocket speeds up. Trouble is, if the rocket gets going near the speed of light, the rocket doesn't speed up like it's supposed to. And this means perhaps the conservation of energy is wrong. It's not speeding up like it's supposed to. You're making the assumption of Newton that the mass doesn't change. You can increase the kinetic energy by increasing the velocity or by increasing the mass. And so what happens is when you get an object going near light speed, the work that you do on it doesn't increase its velocity, it increases its mass. It increases the kinetic energy not by increasing the velocity, but increasing the mass, which means that the work is converted into mass. Work is converted into mass. Work can be converted into heat. Work can be converted into gravitational energy. Work can be converted into mechanical energy. Work can be converted into electrical energy. Conclusion, mass is a form of energy. Mass is solid energy. Mass is energy. In 1905, Einstein concludes mass is a form of energy. And he actually writes an equation that tells you the equivalence between the two. He says, given the mass of the object, if you multiply it by the square of light, speed of light, that is equal to the equivalent energy of that piece of matter. The fact that an object exists and has inertia means that it possesses a self-energy. Now the speed of light is huge, 670 million miles an hour or 186,000 miles per second. You take either of those numbers in whatever units you're at and you square them. That's a huge, 670 million times 670 million is, it's billions, trillions, okay? Trillions. It means a little mass is equal to a huge amount of energy. I mean a tiny amount of mass. It means that, among other things, mass is a potential energy source to run our factories and to run our trains and our cars. That even a small ball of matter contains an unbelievable amount of energy. Okay? And this led to something in World War II which changed the entire status of the planet. If mass is a form of energy, then could you make some sort of an engine? A heat engine takes heat energy and converts it into work. Could you find a way to convert some of that mass into useful work? That's what energy is. Energy is the ability to do work In the 30s and in the 40s, scientists figured out how to do it. The result of that is, for good or bad, nuclear energy. Perhaps one of the biggest everyday results of special relativity in this entire chapter we've been covering is the prospect of nuclear energy. How much energy? Turns out that if you take a ball of uranium, maybe this big, maybe a little bit big, and an orange-sized ball of nuclear material, plutonium or uranium, an amount that you can pick up. You can hold it in your hands. You can hold it in your hands. If you ignite that the proper way, it's not like setting it on fire. You have to do special things. But if you cause a nuclear reaction to occur in a ball of metal this big, the energy released will destroy an entire city. And in World War II, we released that energy both from uranium and plutonium, and we destroyed 2 cities. We wipe out an entire city. Now we have devices that are so powerful using nuclear energy and nuclear explosions that we can build a device that we can fly in a plane, drop it on New York City, and wipe New York City from the face of the planet. One of these devices we detonated in the Pacific Ocean at Eniwetok, and it eliminated the island on which it was detonated. When that device was detonated, the island that it was on was gone, and there was a 2,000-foot deep crater in the Pacific Ocean below it where the device had been detonated. We literally have the ability to destroy ourselves. We have control of this type of energy. And we're not the only ones. There are multiple countries out there now that possess these weapons and have tested them, and we know that if we don't learn to get along with ourselves, we do have the ability to destroy ourselves and destroy many of our cities. So far, it hasn't happened. We've come close. During the Cuban Missile Crisis, we came close. Unfortunately, it did not finally pan out, thank God. But we really came close. And so if anything in special relativity means anything, it is the nuclear energy prospect and E equals mc squared that comes out of it. Now, of course, we can also controllably release nuclear energy. We do have nuclear electric power plants. We have nuclear submarines. We have nuclear aircraft carriers. We have nuclear submarines, aircraft carriers, and so forth, which can stay at sea for many, many months or even a year if we want, because that's all it takes is to charge them up and with the proper amount of uranium, and they'll run for a very, very long time. So, of course, it's available for good or bad, but it is one of the things, one of the legacies that comes out of this in 1905 that we must now live with. Let us stop there. That concludes everything that's going to be on our exam on Friday. Let me talk about that exam. If we are permitted to meet live, we will. And that means on Wednesday, if we are permitted to meet live, we will. If we're not permitted to meet live, then we won't. So the exam on Friday might be live and it might be on Canvas. You'll just have to wait and see. Regardless, the quiz will be online and live, as it has in the past, if we're allowed to be live on Wednesday. If we're not allowed to be live on Wednesday, everybody will take the quiz online. Okay? We'll just have to wait to see. Watch for emails coming out from me. And also, I'm looking for a couple of videos on YouTube that you'll be able to watch in addition to a planetarium show for extra credits. So watch out for those emails. Okay? All right, take care, and we'll see you soon. Bye-bye.